Hello, everyone, and welcome again to our channel of basic engineering. Um, in today's session, I want to go over the analysis of rigid bodies in 2D. So, what is a rigid body? A rigid body meaning the body is not flexible, right? It's like this desk or a building or a bridge. When you come to think about it, there is no such thing as a an ideal rigid body. But for the sake of analysis, you know that if you apply a force on anything, it deforms. And you say, I don't see that. Yes, because the deformation is so small that you cannot see it with your naked eye. But whenever there is a force, there would be a stress, and whenever there is a stress, there would be a strain. You learn that later. But what we are saying that um if there are two characteristics of the deformation, first of all, it's very small. Like I said, you cannot see it with your naked eye. You will not see that, the bridge will deform under the load of trucks, for example, crossing it. So it's very small. That's one thing. And it's flexible, or I would say it's not permanent, it's temporary. Meaning, once you take the load out or off, it will restore its original shape. So, for our case, we are going to deal with beams, with frames, with trusses, as you will see, or machines. And for all of those, we can very simply call them rigid bodies. Notice rigid bodies, if the forces, if am analyzing a specific rigid body and all the forces on it are concurrent, they intersect at a point, then this would be reduced to a particle. I don't care how large or what's the shape of the thing, but if the forces are all at one point, I only concentrate at that point and say I am analyzing a particle. Okay, so before doing that, let's discuss something or two things really that are important. So let me just draw a very simple beam. A simple beam is a beam. Usually we draw a straight line, a horizontal line, and that is the beam. The beam has a span, okay, which is the length, but this beam cannot stay in the air. It has to be supported, okay? So I'm going to show you two types of supports. Maybe on the left-hand side, I would have a pin or a hinge. So that is a pin or hinge. And on the other side, I will have something we call a roller. So a roller, as you can see, it's as if these are wheels. They aren't, but as if they are. So we call that a roller because it allows, if it's alone, it can roll right and left. These are the two most famous. We'll cover more. Now, I want you to understand and ask you how many equations of equilibrium do you think I will have for a rigid body equilibrium in 2D? Remember, when I had a particle in 2D, we had two equations of equilibrium, summation of the forces in the x equals 0 and summation of the forces in the y equals 0. And when we moved to the 3D, we introduced summation of the forces in the z equals 0. We are going also to do the same thing. But what's different? Try to remember what makes the particle a particle and what's the difference between a particle and a rigid body. Think, give you a few seconds, and then I'm going to tell you. We said that on the in the case of a particle, since all the forces intersect at a point, They cannot rotate this body. The body can move right or left, front or back, but cannot rotate, right? But for a rigid body, if I have a force acting like that here, another force like that, they're not concurrent. Okay? So if think about it, if this was a roller and this was a roller, and since this is inclined, this beam would start moving sideways to the left, right? Left, right? Okay. Just kidding. So it's not enough to say summation of the forces in the x direction equals zero and summation. Of course, they are needed because if not, you won't have equilibrium. But they are not enough because these forces can produce rotation. So I have to prevent rotation. But guess what? If we are in 2D, meaning in the XY plane, I can only rotate about the Z axis. This paper can rotate only, it cannot rotate about the Y or the X. Cannot. How? If the forces are in the same plane of the paper, they can only rotate it or move it, but cannot rotate it. I'm sorry, I rotate it only about the Z axis, right? So summation of the moments about the Z equals zero. Usually we drop this subscript. Why? Because it's just summation of the moment in one direction, which is the Z. But since we are not going to use um, vectors, I can say just summation of the moment in the plane equals zero, or, you know. So because I have three things here, three equations, I have to prevent horizontal motion, I have to prevent vertical motion, I have to prevent rotation. So my supports should prevent these three things. Think about it. I don't want horizontal motion. Notice I said that's why I use a hinge. The hinge prevents horizontal as well as vertical motion. This one prevents horizontal motion also, only, but together they also prevent rotation. Huh. Now, when I am drawing the free body diagram of a rigid body, okay, so this is my X, this is my Y. So I have my forces, whatever forces they are, I don't care. But I'm going to replace each support by the forces or the moments they resist. As we said, the roller doesn't prevent horizontal motion, so there is no reaction horizontally, right? It's free to move horizontally. But there is a vertical reaction because this roller cannot move up or down. It's attached to the ground, but it has rollers that allow it to slightly slide right and left, very slightly. Okay, it's not going to run because I have here something. So so if I call this point A and that point B, I would refer to this reaction as B sub Y because it's in the Y direction. It's preventing the motion in the Y direction. So the reaction shows up only when in the direction that the motion is prevented or the rotation is prevented. But those two by themselves, they cannot prove. So each support by itself cannot prevent rotation. Meaning, if I take this one out, this beam would fall down. And if I take this one out, this beam would fall down. But together, they prevent the rotation. Okay? Now, we see that at A, there is no horizontal motion and there is no vertical motion. So I will say a sub x and a sub y. There are three unknowns. Notice we had three equations of equilibrium, so we can solve up to three unknowns. I cannot have less than three. If I have less than three, my structure, in this case, my rigid body, uh, would not be stable. It would be unstable, right? Because if I make two rollers, then you push it and it moves, it runs, right? It's like something that is mobile. But I have to prevent either here or there the horizontal motion. And someone would say, so why don't you make them both hinges? Yeah, I can. I can. And you are going to learn that in a more advanced course, how to find these reactions, because you only have three equations, but in this case, you will have four unknowns, ax, ay, bx, by. So if I use a hinge here, so let's say if the number of support reactions is less than the number of equations, meaning less than three, the rigid body is unstable. You can't have a stable rigid body if you have less than three reaction supports. If the number of support reactions equals three, the rigid body may be stable. You say, what? You just said it has to be three. Yes, I said they have to be three, but I didn't say this is enough. No, you are confusing us. Yeah, that's my goal. I want to confuse you. I want you to think for yourself, right? I want you to have like some, since we can't have conversations, so I'm at least trying to let you think for yourself for a while. How can we have three or more reaction supports, and the beam is still unstable, or the rigid body is still unstable? Yeah, you can think of many, many ways. What if instead of having a hinge or a pin here, I make it a roller and I add a third roller in the middle? I have three support reactions, but nothing prevents horizontal motion, so it's unstable. If I make them 100 rollers, it's still unstable. Huh. So this case is unstable. I'm going to show you another one that also is unstable later. But for now, keep this in mind. If the number of support reactions is greater than three, yeah, it still can be unstable. But most likely the rigid body may be statically independent. I'm sorry, statically stable, statically indeterminate, I want to say, and I said indeterminate. What's the meaning of statically indeterminate? Meaning using statics alone. That's what we are using here is statics, right? Nothing is moving. So using statics alone, you will be unable to determine all the support reactions. So how do you determine it? You have to look at the deformation. Okay? So that's what you will learn in a more advanced course than statics, because statics alone cannot determine everything. So you will never give you this case. right? Because you won't be able to solve it. Doesn't make sense. Now, I'm going to show you another case where I'm going to use three support reactions and the body and the rigid body is still unstable. Okay, here I have my roller. Notice, as I said, the roller here allows for small motion. Suppose this was a bridge or something, or some other like steel beam, and then you come to a day that is extremely hot. What happens to the length of the beam? This beam will get slightly elongated, right? So if those two were hinges, that will develop stress inside the beam. Okay? And I cannot using statics find, the x components and as well as the y components because I only have three equations of equilibrium, not four. So I know that, for example, if there is no inclined load, if these loads are vertical, I would know that the reactions are equal, but I don't know how much is each one, right? So that's why we say the roller here is to relieve that stress. So the body can extend a little bit without being compressed. So if you are trying to keep a length of a beam without expanding and you heat it up, you can feel that it's pressing on your hands, of course, not your hands, but I'm just theoretically talking, okay? So, because you are preventing it from expanding. So that prevention produce internal stresses. It's as if you are compressing the beam and having some stresses and deformation inside the beam. So that's why we cannot, using statics alone, find these forces. Okay, so here if I have these forces, some forces here, and then I have a hinge. I wanted this to be a hinge. I'm sorry. That's my mistake. That's a hinge. And here is a roller. Is this beam stable? No, it's not. Why? Because this is preventing horizontal motion, but it's not preventing vertical motion. So this beam would fall, right? It's going to slide on the wall and fall down. So what do you notice about these two cases? I have three component reactions. Here is the first, AY, BY, CY, A or ACB. Here, I have AX, I have BX, and I have a BY. What do you notice about these two cases? This one is easy. All the reactions are parallel to one direction, so they cannot prevent motion perpendicular to that direction. So I have to have my number of support reaction has to be three, provided that these three support reactions are not parallel, because if they are parallel, they cannot prevent motion normal or perpendicular to that direction. These are parallel to the y, so they cannot prevent horizontal or x motion. But how about those? Those three are concurrent at point B. And if they are concurrent at point B, we learn from particles is that forces that are concurrent, they cannot prevent rotation. They cannot produce rotation, and likewise, they cannot so this beam will rotate about point B. So now we can say when my rigid body is stable and statically determinate. If the support reactions are three, provided there that they are not parallel and they are not concurrent, anything else is fine. I hope this clarified it because I wanted to spend some time on that because that's extremely important. Now, the last thing I want to talk about is what we call two force members. What are two force members? Two force members are members that are connected at their ends only, like this beam, but this beam is not loaded anywhere between in their span. So I may have a beam, uh, a, a member that looks like that, and it's not loaded, okay? But it's connected to other parts of my structure. So the other parts are pushing it and pulling it and whatever. The force would either be compressive or tensile, but at least I know their direction. So they act as one unknown, not two. Because usually you have two unknowns, you have an X and a Y. Now, I don't have to care about the Y since this member is horizontal, so the force, and it's not loaded. If I place a load here, yeah, there is X and Y. But if I don't put any load, maybe except at the ends, then it's inside the member, it's a two force member. The shape of the member is irrelevant. I can have a curved member like that, but if I don't have any loads, then it's a two force member also. Again, tension or compression depends on the loading. So these are the two things I want you to know about the supports. One last thing, how did I forget that? Another type of support that we will encounter would be what we call a fixed support. And this point is A. A fixed support prevents everything. It prevents horizontal motion, it prevents vertical motion, and it prevents rotation. You say, oh, are you telling me that? Yes, if that's a rigid body, of course there would be deflection, meaning there would be a very small rotation that, again, you cannot see it with your eyes. This is not uh, a diving board that will go up and down. No, 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 no. That's a beam that's maybe made of concrete or steel. So it's not gonna fall. It's like a balcony, right? It is it's what we call a cantilever beam. Okay. So, of course, it doesn't have to be very long, depending on the material and its strength and so on and so forth. But that's beyond the scope of the course. What we are talking about is that there may be slight deflection, but remember, we said if it's a very small and it's elastic, meaning it will be relieved if you take the load out, then we consider that a rigid body. But this thing prevents rotation. So if I want to draw a free body diagram of that beam, I would say there is an X, there is a Y, and there is a moment. MZ, of course, but as I said, we don't write MZ because notice these want to rotate counter clockwise, so that resists that by reacting and producing a counterclockwise moment. So these are the three main types of supports: a hinge, a roller. This prevents both motions, X and Y. This prevents only Y. This prevents everything, X, Y, and moment. Okay, now I prepared, or I brought two examples. Okay. In this example, here we will assume that the weight of the beam is negligible. If it was important, I would say, okay, because it has the like um, it's it's having the same cross section all along, then its weight would be in the middle. So I would add a weight here, a load like those. Okay, but this one doesn't have any. And you say, but that's not a beam. There is something. Yeah, that's a hinge. So it has two unknowns. But isn't that also a hinge? So there are four unknowns. That's statically indeterminate? No, it's not. Why? Think about what we talked about here. What do you think BC is? If you said two force member, you are exactly right. Why two force member? It's connected at B, it's connected at C, and I don't see any load. I don't have a load. Even its weight, if its weight is not negligible, notice I'm working with 600 Newton, 800 Newton. So if the weight is, say, 100 Newton, I have to take it into consideration, and this would become a statically indeterminate problem. But it's not. It's a light pipe or something. So I start by drawing the free body diagram as follows. Notice the beam is just a straight line. I have to show, of course, the dimensions and the loads. So in the middle here, well, I can draw the whole thing. Let's do that. Let's draw it. I'm going to show the load here, a load at the end, and a moment. That's a couple, right? I can take it from here, place it anywhere I want. It's the same. 800 Newton, 600 Newton, 1.5 meter, 1 meter, 1 meter, 2 meters, A, B, C. Now, two more things. I have to show the reactions and I have to show my coordinate systems. Why? Remember from the particle, we said if you are going to write some of the forces in the x, you have to tell me where is the x. And you say, okay, x is horizontal. Always. No, not always. Sometimes I may have used this as my x and that as my y in other problems because it's more comfortable. It's easier. Okay? But here, since I said this is the x and this is the y, so I have a force here that, or a reaction is ax, a vertical one that's a. Notice that I'm assuming ax is positive and ay is positive. And if I end up with a negative sign for one of them, it means it's in the other direction. Okay. And then here, I'm not going to say Cx and Cy. I'm not. Why would I make them four unknowns? I know that the reaction here is along the line BC. So I'm going to say FBC, for example. And this is a complete free body diagram because I have everything right there. Now, I have three equations of equilibrium, right? And I have three unknowns, so I can solve. Okay. The first equation of equilibrium is the summation of the forces along the x equals 0. When I write the x, I will have the x component of that and ax. There are two unknowns in this equation. When I write summation of the forces in the y equals 0, I have a y component of FBC and AY. So there were the two equations. Then I have to solve three equations in two unknowns. But if I am clever enough, I can start with the summation of the moment about a particular point equals zero. And that, if I pick my point correctly, I will have to solve for only one unknown. Can you tell me what point works? If you say point A, yeah, of course, because AX and AY meet at A, so they don't produce rotation about A, and I can find FBC because FBC has a horizontal component that is rotating counterclockwise and a vertical component that doesn't produce moment. So I can find FBC very easily. If you tell me I can take the moment about B, you will also be correct because FBC and AX meet at B. So I can find AY very easily through the moment, right? So I think taking the moment about B would be easier. It's not hard. I can decompose that very easily, as you can see. How do I decompose FBC? If you remember, we did some geometry here. This height is 1.5, and this width is 2, right? Meaning, if you multiply them by 2, the ratio is 3 to 4, meaning that would be 5. In fact, the length of BC is 2.5 meter. You can easily find it. That's a Pythagoras triangle. 3, 4, 5. So the horizontal component is 2 over 2.5 or 4 over 5. So you could have said this is 4/5 FBC and this is 3/5 FBC. So I could have used that much easier and take the moment, say here, and say 4/5 FBC times 1.5 is a positive moment about A. I think we'll stick with B. Still, it's easy. Now, if I take the moment about B, then FBC and AX don't produce moments. But AY does, the 600 does, the 800 does, and this 900 Newton meter does, because it's already a moment. It's a free moment. You can take it from here, place it at B without changing anything as you learned before. That's a moment of a couple. So remember, clockwise. So here um, we can say, some people do that, meaning if it's to the right, it's positive. If it's up, it's positive. If it's counterclockwise, it's positive. So just to show what we are using the normal thing everybody is using. So now let me write this equation. If I start from the right, I have a clockwise moment of 900 rotating about B, so negative 900. The 800 is a force 2 meters away. It's still rotating clockwise, so minus 800 times 2, which is the perpendicular distance from B. And then I have a 600 rotating counterclockwise. Notice, some people say this is a negative moment because the force is going down. No, because the rotation is clockwise. 600 is also going down, but it produces a positive moment. So plus 600 times 1. Anything else? Yes, the AY. The AY is rotating clockwise, so minus, and the distance is 2 minus 2AY equals 0. So if I move AY to the other side, I get 2AY equals negative 900, negative 1600, plus 600 equals negative 1900 Newton. So AY equals negative 950 Newton, meaning it equals 950 Newton going down. That's the negative sign, means it's going down. So now you don't need to redraw this going down. We already know that. So now, because I know AY, notice if I take summation of x equals 0, I have FBC and AX, two unknowns. So I move to FY. Notice you don't have to take them in the same order. See what makes the problem easier for you. Okay? Like when we saw here, X would have two unknowns, Y would have two unknowns only the moment at a clever point, which is either even at C, I could have taken the moment about C. Why? Because AY passes through C and FBC passes through C. The only unknown would have been A sub X, and I could solve for A sub X. I could take the moment about A, about B, about C. It doesn't matter. All of them would be easy. So now I'm going to move to the Y direction. Why? Because the only unknown now would be FBC. In this case, I would say AY, which is negative 950 because it's going down, minus 600, minus 800. These are all the forces going down. But then I have 3/5 FBC going up. So plus 3/5 FBC equals 0. So 3/5 FBC equals this plus this plus that. This plus this is 1400, 2350. Multiplying both sides by 5/3. This is not uh, divisible by 3, so it's easier just to say 2350. Is that correct? Yeah, 14, 2350 times 5/3 equal 3916.7 Newton. And it's positive, meaning I assumed it's correct. It is in this direction. That makes a slope of 3 to 4. So you don't have to, but you can say 3, 4, 5. But that's FBC. So now I know AY, I know FBC. The last thing is the summation of the forces in the X. I don't have an X. I don't have an X. That's a moment, so it doesn't have neither an X or a Y. I have A sub X going to the right plus 4/5 of FBC equal 0. These are the only two forces in the X. Notice this is this would move to the right, so it would be negative. So AX would be this number, but in the negative, times 4/5 equals 3133.3, or 3133 is good enough, meaning 3133 Newton to the left. And that is how I solved the problem. The three unknowns that I had in the original problem, I found their values, and the values don't, some usually, I mean, if you write this 3920, 950, 3130, that would be good enough. I mean, it's not like zero point 0.3 Newton. We know we have a lot of approximation. This length is not exactly 4 meter. This weight is not negligible. This weight is not negligible. So don't please tell me how many decimal places should I use? Should I use 5 or 6 like in this? No. This is approximate, right? So anyway, this was long enough, so I don't think I'm going to go over the second example, maybe in the next lecture, or I should have made only I didn't want to just go over the reactions and then the next session would be examples because you may forget what we said. So I wanted to do that So I apologize if this was a little too long. I will have a very short one where I will solve another example, and that would be it. Again, sorry for the long session, and I hope that was easy for you to follow and understand, and hope to see you soon. Bye.